Hey, let's get started. I think almost everyone finished the homework 3.1 that was due last night. I moved it back. This extra credit assignment, this test number 1 review, I moved that back till tomorrow, so that's due tomorrow. And then there's this quiz on these two homeworks, this short quiz on these two homeworks, due Friday. So I put that to Friday. Now, there's been a lot of confusion. Well, I don't know about a lot of confusion. There's been confusion on the quiz because, so I'd mentioned this before, but originally quizzes, the way quizzes should work, okay, is that you get 5 submissions, but you have to submit the entire quiz. So you should see just the submit button at the bottom, all right? So you have to answer all the questions and then submit, and then go back and, you can still resubmit the quiz, but you have to submit all at once. You cannot submit one question at a time to check it like it is on the homework. So that's why the submit button is on the bottom. However, that's a setting that I have to switch, and I think on the initial quizzes I had it where you could submit one question at a time. So on this quiz, when I made it so you had to submit the entire quiz at once, then that was causing confusion. Okay. So what I will do is, since it's not due till Friday, I will go back and up the number of submissions. I will increase the number of submissions, which is set to 5. So I'll increase the number of submissions, but I'm still going to keep it to where you must submit the entire quiz, okay? So I will up the number. So if you run out of submissions, I will double that or something to 10, but you still have to submit the entire quiz. So go through the entire quiz, try answering all the questions, submit it, and then go back and the ones you missed, try fixing those, and then resubmit the whole thing, right? Okay, up to 5 additional times. To get that quiz score, all right? Because that's the way the quizzes were originally designed to work, all right? A little bit more restrictive than the homework assignments, okay? So then this homework 3.2 is due, supposed to be due next Monday. We'll see how far we get today. This homework you should be able to finish. And then we'll see how far we get today in the notes so that you can start this homework on what's called marginal analysis, which would be due at the test. And that's the last thing that's on the test, okay? And so remember, we have a test on next Wednesday, right? So a week from today is our test. And so the test review is posted, okay? So if you go to the Blackboard page under the sample test link, you can print out that test review. The answers aren't there yet. We won't put those up until maybe next Monday, okay? But the sample test itself is posted. And I think after today, you should have everything that you need, at least to get through the sample test questions. That marginal analysis homework, the questions there are a little bbit more challenging than the questions on the sample test, okay? But the test will look like the questions on the sample test, okay? I think after today you'll probably be able to do almost all of that test review, okay? So it's a good thing to do over the weekend, okay? While you're finishing your 3.2 homework. All right. John, did you schedule a test review yet?
Yes.
Oh, okay.
Test review is going to be on Friday from 10 to 12 in South 405.
Okay, so Friday from 10 to 12 in South 405. But you're also available on Monday at your regular time, right?
Yes.
Okay. After class. So if you miss Friday, then you can also come back on Monday, South 405, and get help with the test review. Okay. All right. So that's about where we are on the assignments. let's talk about some our notes today, and then so we can get as much of that done as possible. And then Monday, we'll have more time then on Monday to answer homework questions, look at the test review in class, and make final preparations then for the test on Wednesday. Okay. Here are a couple of problems in the notes from that section 3.2 that we didn't get to last time. Okay. And so let's look at these. You're going to need a calculator for a problem like this, so it helps if you have a calculator here to help you here. All right, so it says a model. So that just means usually in this class some sort of formula or function. So a model for the balance due on a certain credit card is given by this particular function. All right. So this is called an exponential function. And notice there that in this function you have the input variable here is d. The name of the function is f. The input variable is d, and that is in the the exponent of a power, right? Okay. So so usually we refer to functions like that as exponential functions. So and the d here represents the number of days after the due date. Okay. And it doesn't say it here, but the output from the function here, since this is balance due on a credit card, I think the output from the function here is just dollars, okay? So it doesn't indicate that. So the very first question is not a calculus question, really. It's just more of an algebra question. It just wants to know how much is owed after 30 days after the due date. So that's an easy question to answer. All that's asking you to calculate there is f of 30. So I think the reason for asking that question was just to get you used to substituting numbers there into this exponential function and doing the evaluation. Let me make sure I wrote down that formula right, though, because that looks... this is an example that I took from the book, so I can check here. Yeah, that's right. Okay. So I think the purpose of this question was just to help you get used to evaluating an expression like this, 2,000 times 1.00062 raised to the 30th power, okay? You're thinking that 1.00062 raised to the 30th power might be a really big number, but actually it turns out to not be that big of a number because this is very close to 1, right? And when you raise 1 to any power, you still get 1 again, correct? So so you're not going to really get a number here that's that gigantic, okay? If the base here were a little bit bigger, raising a base to the 30th power might give you a really large value, and your calculator might not be able to calculate it, but in this case, I think not so bad. But remember now, it's the 1.00062 that's getting raised to the 30th power, okay, and not the 2,000 in front. So if you raise the 2,000 to the 30th power, that is going to give you a big number. So on a calculator, it depends on the calculator how you would enter this, but often on many calculators you can use the caret key, all right, to raise a number to a power, okay? So you might try using the caret key on your calculator, or on some calculators you might use the x to the y key, or sometimes it's y to the x key on the calculator to raise a number to an arbitrary power, okay, like this, all right? So if you're having trouble using your calculator, you may ask me, and we can probably figure out how how to raise that number to that power, okay? But that's the first thing you want to do is raise the 1.00062 to the 30th power and then multiply that by 2,000, okay? In the order of operations, exponents come before multiplication. So don't multiply the 2,000 in first and then raise to the 30th power. That's not going to work. Take the 1 point, etc. here, raise that to the 30th power first, and then multiply by the 2,000, okay? I think that approximately comes out to be, but you can check this, $2,037.54. Were you all able to confirm that? Okay. All right. So once you raise the 1, etc., to that power, and then multiply by the 2,000, that should be approximately what you get. See, so it's not really, you don't get a really gigantic value here, right? Okay. So the interest apparently on that balance for that 30 days, right, is only amounting to, well, that's still a substantial amount, but it's amounting to 37 and 54. Okay. All right. Now, here's the calculus part of the question. They want us to find the derivative of this function f. Okay. So we have to remember our derivative rules. Let me show the function f. So we have to remember the derivative rules for our exponential functions, right? Okay. And so f prime of d is going to be, you're going to keep the 2,000, just that constant multiple, okay? And remember, for exponential functions, the derivative is just going to repeat the function itself. So in the derivative, you'll get also the 1.00062 raised to the d power, okay? But you have to make now one slight adjustment, okay? If this were just e raised to the d power, so if that base were e raised to the d power, then the derivative would just be e raised to the d power, okay? But when the base is some number other than e, remember e is about 2.718, so this is not e in the base, right, okay? Then you have to adjust your formula slightly by multiplying in the natural log of whatever that base is. So we're going to have to multiply in here the natural log of 1.00062, okay? And that's it. So it's a really easy derivative formula for exponential functions, but just remember, you have to, so the formula for the derivative will be the same as the function itself. So that's kind of really unique about exponential functions. But you have to multiply in the natural log of the base. Actually, this same rule applies even if the base is e, because the natural log of e turns out to be exactly 1. Okay? So even if you multiply in the natural log of e, the rule still works. But the natural log of e is just 1, so it doesn't contribute anything to the formula, to the derivative formula. But in this case, the natural log of 1.00062 will not be quite equal to 1, all right? And so on your calculator, then, you can get an estimate for the natural log of 1.00062, okay? And you'll need a calculator for that. Okay, you're definitely not going to be able to do that without a calculator. What does that turn out to be? Can someone take that natural log for me? So all scientific calculators will have a natural log key, so it will be easy to calculate and get an estimate for that natural log. Approximately, what is that? The natural log of this is 0.00062? Really? All right, so say that to me again. But I got to get me the zeros. What? 0.000 zeros? Oh, okay. And 61987? Ah, so it is 0.62. Now that's kind of no. Okay. Okay. All right. I think we've got some confusion here. All right. Let me check it on my calculator. So 1.00062, and then I'm going to calculate the natural log of that. Oh, so you're right. Okay. So it is 0.000619807. Is that y'all didn't get that? No. Okay. I just typed in the 1.00062, yeah, okay, and then just hit the natural log key. So what did you do?
We're getting the same thing, but it's just that it's raised to the negative 4 power.
Oh, it's giving it to you in scientific notation. Okay, right. So, oh, I see. So you're seeing, so you might be seeing 6.19807, and then it puts a -4 over there. Yeah. Okay. What that -4 means is that's in scientific notation. So you have to take that out of scientific notation by shifting that decimal place, and the minus means you're going to shift it 4 places to the left. Okay. So when you shift the decimal place 4 places to the left, you get 0.000619807. Okay. So be careful about the notation there. All right. Yeah. So your calculator is giving you scientific notation. Of course, it doesn't, which is this. Of course, it doesn't write the times 10. All right. But that's what that -4 means. Okay. And so to convert that out of scientific notation, you would shift the decimal place. Because this is a negative exponent, you shift the decimal place back to the left. Okay. So indeed it is or very close to 0.000619807, and so we can round that off to about 0.00062. Okay. I was a little bit surprised because those look alike, all right? And I wasn't expecting that. And now you can multiply, if you want to, you can multiply that by the 2,000, okay? So you can take that and multiply it by the 2,000. And so that comes out to be 1.239 6 or something like that, 2, something like that, times 1.00062, again raised to the d power. Okay. So that's a little bit of an approximation because there are lots of decimal places actually. Lots of decimal places in this natural log, so I rounded this off a little bit. So this is only an approximate value, but that's really close to the actual value for the derivative. Okay. So this is the actual formula for the derivative. Okay. This is just the approximate formula for the derivative because the natural log of 1.00062 is not exactly what I wrote there. Okay. But that's correct to several decimal places. All right, so there's the formula for the rate of change, and now then we can use that to answer rates of change sort of questions. So it asks there, how quickly is the balance changing? See, that's a rate of change question. How quickly is the balance changing after 30 days? So in other words, they want you to calculate f prime of 30. Okay. So just take the 30 and plug that into the rate of change formula. And so evaluating that rate of change, of course, is going to be very similar to evaluating the original function, right? Okay, because the rate of change function looks a lot like the original function because of the fact that this is an exponential function, but slightly different because the coefficient here in front here is not 2,000 anymore, right? It's a little bit smaller. And when you evaluate that, you get approximately 1.26, okay? So rounding off to a couple of decimal places, this is about 1.26. So just a little bit bigger than 1.23 because 1.00062 raised to the 30th power is a little bit bigger than 1, right? So you're going to take this number and multiply it by something that's a little bit bigger than 1, not much bigger than 1. And so you just get a number that's a little bit bigger than the coefficient, but only a couple of pennies bigger than the coefficient, right? Just approximately 1.26. So how do we interpret that now? Okay, so if I asked you to interpret that on the test, right? Okay, what would be the interpretation? So this is a question you could actually answer on the first test, okay? But it's still one that you want to be able to answer for the second test as well, right? Okay, so this is a rate of change you're interpreting, right? Okay, so you would say, but it's an instantaneous rate of change. It's not an average rate of change. So you would say at d equal 30, or that's kind of awkward to say d equal 30. So you might want to say after 30 days, right? Because that's what at d equal 30 means. So after 30 days, what? What's changing? The balance, right? Okay, so the balance is changing, and is it increasing or is it decreasing? Increasing, right? Because this is a positive change, right? So the balance is increasing by, this is dollars, right? Because this is a credit card balance. So it's $1.26, and then don't forget, you have to finish it off now with your rate, okay? So it's increasing by $1.26 per what? Per day, right, yeah, because our input is measured in days, correct? So another way of thinking of this is after 30 days, you're paying about $1.26 interest, right, each day on that unpaid balance, okay? But that's after 30 days, okay? Because each day the balance is increasing, so each day the amount of interest you're going to pay is going to increase as well. So this is the amount of interest you're paying after 30 days. After 40 days, you'd be paying more interest, right? After 60 days, you'd be paying more interest, and so on and so forth. This rate of change is not steady, okay? This is not a linear function, so that amount of interest you're paying is increasing, unless, of course, you're paying down the balance, all right? Let's look at one more example. There's a question like this in the homework. This one's kind of confusing, okay? So you know when you're on a diet, right, you don't want to lose weight too rapidly because that is not healthy, okay? So this formula is presented as sort of what's the optimum maximum weekly weight loss, okay, that a person should achieve on a diet, okay, so that they won't, be doing something dangerous to their health, okay, on the diet. And so there's the formula. The W here now is represents the weight of the person, but it's not just the scale weight of the person. It says in this, so you have to read this kind of carefully. It says in this formula, W plus 130 is the dieter's body weight. Okay, so if a person weighed 150 pounds, then in the formula you would use 20, okay, right? You would plug 20 into the formula to calculate their optimum weekly weight loss because 20 plus 130 is 150, okay? which is their scale weight. Okay, so you have to look at that part kind of carefully. If you plug in just the weight on the scale, you get much too large a value here for the optimum weekly weight loss. Okay. All right. So it's not a difficult formula, but the only thing that's interesting about the formula is it has that natural log in it. Okay. As part of the formula. Actually, I graphed this one. Let me see if I can find the graph. It's on this tab. Yeah. Okay. So there's the graph of that. There's the graph of that formula. In the formula, by the way, the values that you're supposed to use for W are only 10 to 90. So I only graph this. Formula from 10 to 90. So what that means is this formula only applies to people who weigh between 140, because 10 plus 130 would be 140, up to people who weigh, what's 90 plus 130? 220, okay? So up to people who weigh 220, okay? And so you can see that that optimum weekly weight loss increases, right? As a person's weight increases, but it increases rapidly at first, but then up here it doesn't increase as rapidly, okay? Because the graph there starts to flatten out, right? As the W values increase, okay? So as you already can see, right, from the formula, that graph's not a straight line, right? Because it involves that natural log. So. All right, so let's go back there and answer a couple of easy questions. So the first one, again, is just an evaluation problem, so really straightforward. It says, what's the optimum maximum weekly weight loss, okay, for someone who is weighing 200 pounds, okay? So someone who's weighing 200 pounds, they want to go on a diet, okay? And so they go to the doctor, nutritionist. The nutritionist gives them a diet, but the nutrition warns them, okay, you don't want to lose too much weight per week, right? Okay, so don't overdo this diet. Don't starve yourself, all right, because that's dangerous to your health, okay? The losing weight is good, but starving yourself is not, all right? So to determine what that optimum amount is per week, the nutritionist would use a formula like this one. Maybe not this exact formula, but a formula like this one. So let's calculate what that optimum weight loss is, okay, for this person. So it's minus 1.875, right, plus the 1.284 times the natural log. But here's where you have to be careful. What are we going to plug in for W? Not 200. Okay, 70, right? Okay, that's what I was warning you about here, because in this formula, W plus 130 is the actual body weight. So for someone who weighs 200, that's 70 plus 130. So what you would plug into the formula is just 70, okay? So if you actually plug the 200 in here, you'll get much too large a weight loss value, okay? And now you just have to rely on your calculator to there to give you an approximate value for the natural log of 70, okay? That's going to be a fairly large number, and then multiply that by 1.284, right? Okay, and then you're subtracting, because this is a negative coefficient here, so you're subtracting the 1.875. What does that turn out to be? Someone have that calculation? 3.007? Okay. So can we round that off to 3.58? Is that okay? All right. So 3.58007, 3.58, close enough, right? Actually, probably 3.6 there would be close enough, right? Okay. So so this person shouldn't really lose more than about 3.5 pounds a week, right? Okay. Pretty tough to achieve that, right? But that would be the maximum that you would want to lose. Anything more than that per week would be considered unhealthy, okay? All right. Now let's answer the second question here, okay? So how is that that optimum weight loss changing for someone who weighs 200 pounds? Okay, so that's a rate of change question, and to answer that rate of change question right, you're going to have to know what the derivative formula is. Okay, so let's go back to our original function and let's write down the derivative. Let me write it down up here, and then we can use that. To answer that last part. Okay, so I'll express the derivative as dy over dx. Remember, that's another way of writing down rate of change. Okay, or you could also write. There are lots of ways you can write down rate of change. You could also write down y prime. Okay, as the weight of change, as the rate of change. Okay, not weight of change. Okay, but rate of change. All right, so let's see if we can apply now our knowledge of differentiation to easily find that rate of change formula. Well, what's the rate of change of that first term going to be? Zero, right, because that's a constant, right? Okay, see that first term, the minus 1.875, doesn't involve the w, right? W is the variable here. So that first term doesn't involve the w, so that's easy to differentiate. That just turns out to be 0. Okay. Now, what about the second term that does have the w in it? So you're going to keep the coefficient of the 1.284, right? And that won't change. But what is the rate of change now of the natural log function? So that has a very easy rate of change. You remember that? That's exponential, okay? But for natural log, it's just so easy you've forgotten it. It's 1 over, right, yeah. So the rate of change of natural log of w is 1 over w. So very easy there. For the natural log function, the rate of change is just 1 over the whatever the variable is, okay? So just 1 over w. So we end up here with a very easy formula. It's just 1.284 there divided by w, okay? What could be easier? And so we wanted to find the rate of change for someone weighing 200 pounds, right? Okay. So we would evaluate this rate of change. I should have written dy over dw because the variable is w, not x. So we're going to evaluate this rate of change when w is equal to what again? 70, right. Okay. So the way you express, this is very old-fashioned notation. If you're using this notation for the rate of change, then to evaluate it at a particular input, you put this long vertical bar and then write down the input there as a subscript. So you write dy over, I didn't write dx because the input variable is w, not x. So dy over dw evaluated when w is equal to 70. So that's going to be 1.284 over 70, just that easy. So pretty small number there. I think that works out to be 0.018. So what does that tell us? Well, that tells us that, let's see, if your weight changes from 200 to 201 pounds, right, then your optimum weight loss would go up by how much? Yeah, 0.018, okay? So at a weight of 200 pounds, the optimum weekly weight loss is increasing by 0.018, okay? So at a weight of 200 pounds, the optimum weight loss increases by 0.018. That's pounds. Here's what's a little bit tricky. It's pounds per what? Yeah, that's what it's very easy to say per week, okay, right? But it's actually pounds per pound of body weight, okay, is the correct interpretation there. Because what's the input here? See, you're always going to go per unit of the input. And what's the input here? The input here is not weeks. The input here is what? What does the W represent in a sense? What? Yeah, it represents the person's body weight, right? Okay. So what that tells you is, again, when your body weight, if you're weighing 200 pounds and your body weight increased by 1 pound, then your optimum weight loss would increase by about 0.018. You could lose a little bit more if you weighed 201 pounds rather than if you weighed 200 pounds. Okay. That per in the rate of change always is per 1 unit of whatever the input unit of measure is. It's very tempting to say per week there, though. I know why. Okay. All right. Okay, we're going to switch gears here, and we're not going to talk about weight loss. We'll go the other direction. Let's talk about eating Girl Scout cookies, okay, which probably won't cause you to lose weight, all right? We're going to look at applications of calculus now to business and economics, okay? So y'all are all business majors, so this is particularly pertinent to you guys, okay? Especially when you take your economics class, which is you have to take 6 hours of economics if you haven't started doing that already, okay? So in business and economics, of course, the study of cost and revenue and profit when you're producing and selling goods and services, that plays a central role, right? I mean, that's what business is, right? That's producing and selling goods and services. And when we apply mathematics, but in particular calculus, to the study of cost and revenue and profit, that is called marginal analysis, okay? And so, and calculus plays a really important role in the study of cost. And of course, what you want to do with cost is make cost small, right? So calculus plays an important role in the study of minimizing costs, but also in the study of revenue and profit, the revenue and profit you make when you sell whatever goods and services it is that you might be selling, right? Of course, we don't want to minimize our revenue and minimize our profit, right? We want to go the other direction with revenue and profit. We want to maximize revenue and we want to maximize profit, okay? And so calculus can give us tools for help us understand how do we maximize revenue and how do we maximize profit. Now, I've got to distinguish here between revenue and profit. Revenue is the money you generate from the sale of goods and services. That's just the total amount generated, but that's not the same as the profit, okay? Because profit takes into account whatever your costs were, all right? So profit is what you make when you take your revenue, that's the amount you generate, and subtract off your costs, right? Okay? So revenue is just the amount you collect, but profit is the amount you collect above what you paid to produce, whatever item it is that you're producing. Okay? All right, let's take a look at some examples here, and we've got to introduce some terminology because the terminology of calculus in business and economics is different than it is in a math class. Okay, and so you've got to get a little bit used to that terminology. All right, so suppose we're selling Girl Scout cookies, okay? And let's make some simple suppositions here so we can come up with some nice examples. So let's suppose now that in making these Girl Scout cookies, we have, to manufacture these cookies, we have a fixed cost of $200,000. So fixed cost means cost that you're going to have to spend before you actually manufacture a single cookie, all right? So these are costs like purchasing space, right, or purchasing the equipment that's required to make the cookies, okay? These are costs that you are buying insurance, okay? These are the costs that you have to incur prior to actually producing a cookie, all right? And so we're going to assume that in this example, those fixed costs are $200,000, okay? So you can think of those as initial costs or startup costs also, all right, for producing the cookies. And then let's suppose now we have variable costs of $270 per box. That's the actual amount that you spend to make a single box of the cookies. So that is the material that goes into producing a box of the cookies. Okay, that's what we'll call the variable costs. So let's assume that's $270 per box. So that's the amount of flour and sugar and labor, okay, and the packaging that actually goes into a box of the Girl Scout cookies. That seems a little bit high to me, I think. I don't think you want your variable cost to be $270 per box because it's going to be hard to make a profit, I think. But nevertheless, that's what we have in this example. Okay. All right. So first question, very simple here. Let's write down a function that outputs the cost, the total cost. Okay. I should have said total cost there. The total cost. And let's calculate our total cost in millions of dollars because we're already starting with a big amount of fixed costs here. So what's the total cost in millions of dollars for producing Q million boxes of these cookies? Okay. The reason I'm using the variable Q here is for quantity. Okay. So we're producing a certain quantity of these Girl Scout cookies. Let's calculate based on just these assumptions what our cost would be. The way we normally denote a cost function is we use the letter C, okay? And, of course, our input variable here is Q. That's the million boxes of cookies that we're going to produce, okay? Now, I want, so that I don't end up with just really huge values here for my output, let's make sure that when we get our output from this formula, it's going to, our output comes out in millions of dollars, all right? Otherwise, I'll be dealing with really large numbers, and that's going to be a little bit cumbersome, okay? All right, so we want our output to come out in millions of dollars, and our input is also going to be measured in millions. So this Q is millions of boxes of cookies. Okay, all right, so how do we write down this formula that we can use to calculate our total cost? Well, remember, you've got to start with your initial cost because you've got to make this investment before you can even produce a cookie, right? Okay, so that's buying the equipment, right, and the space that's required, and so on and so forth, just to produce a cookie. So that will be part of your total cost, right? Okay, and so we got to write that into our formula. Okay, so let's write down the 200,000, but we want to express that in millions of dollars. So what's 200,000 written in millions? 0.2, right? Okay, so there's our first part of our total cost, right? Okay, we've got to spend that $0.2 million, right, which is $200,000, just to get started on producing the cookies. Okay. Right, now, once we start running our factory, right, okay, then we're going to start making these boxes of cookies, right, and so that's going to be our variable cost, right, that we're going to add in here, and that's pretty easy to figure out, right, because each box costs us what? $270, and how many boxes are we making? Q, million, right, so altogether, how many millions of dollars will we spend on manufacturing those cookies? Well, I think it's just 2.7 times Q, right? Okay. Each box of cookies, right, is costing you $270. So each million is going to cost you 2.7 times the million, right? There it is, okay? So not too complicated, right? There's your total cost function, right, for manufacturing those cookies. That's about the simplest example of a total cost function that you could devise, okay? So in very simple examples in business and economics, when they're asking you to think about total cost, they'll give you very simple examples like this one. But in reality, cost functions are usually a lot more complicated than this. Yeah, all right? So this is just a simplified example. Yeah. That is our startup costs, okay, right? But we remember we wanted to get so we wouldn't come up with really big numbers here. I didn't want to write down the 200,000 in my formula, so I converted all my costs to millions of dollars. So I wrote the 200,000 in millions. So just take 200,000 and divide it by a million, and you get 0.2. Okay, yeah. So this is 0.2 million, which is 200,000, right? Okay. And remember, we're producing millions of boxes. So you take the 2.7 times the millions of boxes, and that will also give you millions of dollars, right? Okay, so your output will come out in millions of dollars. All right, so there's a very simple example of a super simple example of a total cost function. Now let's look at something that's a little bit more realistic here. Okay, all right. In reality, a total cost function may look something more like this. Okay. All right. So so here I've written down a more realistic total cost function, and it's still applied to this example. Okay. So let's suppose that the cost for producing that Q million boxes of cookies. This should be boxes of cookies. It's not just cookies, but it's boxes of cookies. Suppose really to calculate the cost, we're required to use this formula, okay, to calculate the cost. So we have a much more complicated formula to calculate our total cost, all right? Well, let's see. First, in this formula, what are the fixed costs, okay? So how much are you going to have to spend if you don't produce any cookies at all, okay? In other words, if you produce 0, you would still have to spend how much? Well, that's easy to find. Just calculate C of 0 here, okay? Just what's the cost if I don't produce any cookies at all, right? Okay? And so if you plug 0 in this formula, what do you get? Yeah, you get 0.2. That's the fixed cost, okay? That's going to be the cost if you don't produce any cookies. So it turns out to be exactly the same in this formula as it was in the first example, okay? Our fixed costs are still 0.2, okay? But now what's really difficult to answer for this formula is, what is the variable cost per box, okay? That's kind of obvious in the first formula. It's the slope, which is 2.7, okay, right? But in this formula, very difficult to figure out what is that cost per box, okay, of cookies. And in fact, the reason that's actually an impossible question to answer, because that variable cost is actually going to change. Let me show you here a graph of the cost function. So there is actually a graph of that a cost function, okay? And so notice, when you look at that graph and think about what's happening to that graph, see, it's not increasing at a steady rate, okay? So you can see that at first, your costs are not increasing very rapidly, right, as you produce more boxes of cookies. But what starts happening over here as you really start ramping up your production? What happens to your costs? Yeah, they really start going up really fast, right? Okay. So what that means is the cost of producing a box of cookies is getting higher and higher in this example as you produce more and more cookies. Not initially, okay, right? Okay, not initially, but eventually your costs really start increasing very rapidly. Why might that be true? Okay, that's not always true, but why could that be true? Well, think about it here. if you're really producing a lot of cookies, you're going to have to start going out in the market and buying a lot of what? Supplies, right, okay. Well, when you start going out and buying those supplies, sugar and the flour, you're increasing the demand for those supplies, okay? And as you start increasing the demand for an item, for a commodity, then the producers of that commodity will say, whoa, okay, I have a lot of people that want to buy this item. I can raise the price, you see, okay? So by increasing, demanding more of the supplies that go into making the cookie, you may be inadvertently there causing shortages and so forth, and making the price of those commodities go up. All right. So in this case, the variable costs are not constant, right? It actually costs you a little more as you start producing more cookies than if you produce fewer cookies. So I really can't answer the question, what's the variable cost? That's really not a fair question to ask, because the variable costs are not constant, okay? In this example. We're going to come back to that question now in just a second, but let's start with something now that's a little bit easier, okay? So you got to help me with your calculator now, all right? Okay. First is just evaluate and interpret C of 2, okay? So let's see if we can just use the cost function to do something here, all right? So, of course, to evaluate C of 2, right, you're just going to plug C of 2 into the formula, right? And you have to go through the arithmetic. Shall I go through the arithmetic? Try that for me. So try evaluating there C of 2. But what is C of 2 telling you? Yeah, what's the total cost for producing 2 million boxes, right? Okay. So C of 2 is the total cost for producing 2 million boxes. Y'all get a value there? Say that again? 3 point what? 52? Ah, okay. And now remember, that's not $3.52 because the output here is millions of dollars, right? So if we produce 2 million boxes, then our total cost is $3.52 million, right? That was our fixed cost, right? Plus the cost that we had to incur to buy the flour and the sugar and the material and hire the labor, right, for producing the 2 million boxes. So if it costs us $3.52 million altogether to produce those 2 million boxes, then what's the average cost per box? So you made 2 million boxes. It cost you $3.52 million to produce those 2 million boxes. So on average, how much did you spend for each box? How would you calculate that?
3.52 divided by 2.
Yeah, there you go, right. Okay. just take the 3.52 million, right? Dollars and divide it by the number of boxes you produced, right? Which was 2 million boxes. And that would give you the average cost per box. Well, those millions are going to cancel, so you just get here 3.52 divided by 2, and that's your average cost per box. So what does that turn out to be? What? 1.72. Oh, 6? Okay. Well, that's kind of important there. So if we are going to manufacture 2 million boxes, right, then we'd like to be able to sell them for more than 176 per box, right? Because if we don't, then guess what? We're going to be doing what? Losing money, right? Okay. So we know we're going to have to price them more than $1.76 per box, right? Or we're in trouble. We're going to be losing money. So what's a formula for the average cost per box? Okay, so if you wanted in general just to calculate the average cost for a box of cookies, how could you do that? That's right. We're going to call that average cost function. I'm going to write that with C, but with a bar above it there. We often use that to denote average in mathematics. So this is what I'm going to use to denote the average cost. And the average cost is just your total cost, right, divided by the number of boxes you produced, right, which is Q. Okay. So just take your total cost and your total cost and divide it by the number of boxes you produce, and that will give you your average cost per box. Now you might say, but this is for millions, right? And that's true, but keep in mind this is millions of dollars, and this is million boxes. So the millions are going to wind up canceling each other, and you'll end up with just the average cost per box there. Okay. So that's called the average cost function, and that plays an important role in marginal analysis as well. So far now, we haven't done this. None of this is calculus. Okay. All of this has just been very straightforward, just arithmetic and algebra. But now let's introduce calculus in this, and that's what we're asked for in this example. It says write the formula for the marginal cost function. In business and economics, derivative or rate of change is referred to as by the prefix marginal. So if you see marginal cost or marginal revenue or marginal profit, what they mean is the rate of change of the cost or the revenue or the profit. Okay? So let's find the formula for the marginal total cost here. All right? So that's going to be just the rate of change of the cost function. Well, we got to remember what our cost function is, right? So let's scroll back up here. Ooh, we have that terrible cost function. All right? So let's see if we can write down its rate of change. And again, that's referred to as the marginal cost function. All right, so let's see. Can we apply our rules for derivatives here to find that marginal cost? I think so. That's pretty easy, right? Okay, except for the decimals kind of mess things up. So what about for that first term? What's the rate of change of that first term? Yeah, you just bring the 3 down, right, and multiply it by the 2, 3, right, okay, and then subtract 1 from the exponent. So it comes out looking kind of nice there, right? You just get 0.69 q squared, okay? So 3 times 0.23 is 0.69, and then subtract 1 from the exponent. What about for the second term? You just bring the 2 down and multiply it by the 0.98 there, so I think that comes out to be 1.96. and then subtract 1 from the exponent. So you just get q to the first power. And what about for the third term? What's the rate of change there? Yeah, just 2.7. And, of course, what's the rate of change of the 0.2? That's 0, right, because that's just a constant. So notice your marginal cost function there is pretty simple. Well, not pretty simple. It's still a little bit complicated, but it's less complicated than the original cost function, right? Okay, so the marginal cost function there not so bad. Okay, you'll have that written down because let's repeat it down here in the notes. So here's our marginal cost function was, what was that? 0.69 q squared minus 1.96 q, right? And then what, plus 2.7? Yeah. Plus 2.7, okay. So again, whenever you see marginal, think rate of change, all right? In business and economics, marginal always is going to refer to rate of change. And you can apply marginal to lots of different types of functions in business and in economics, but invariably they mean rate of change. So that's why this whole subject is called marginal analysis, because we're using rate of change there to study cost and revenue and profit functions. Let's evaluate that. Let's evaluate that marginal cost function, and let's see what that's actually telling us. So let's evaluate C prime of 2. Well, the evaluation is really easy. So that's 0.69 times 2 squared minus 1.96 times 2, and then plus the 2.7. So I get 0.69 times 4, and then minus 1.96 times 2, so I think that's minus 3.92, and then plus 2.7. So what does that simplify to? What now? 1.54? All right, so that's an easy value to calculate. The interpretation, though, is a little bit, the interpretation is always with these rates of change is the tricky part, okay? So you can get the first part, right? So this is at Q equals 2, which means what? When we are producing how many boxes of cookies? 2 million, right? What's changing? So this was marginal what? Marginal what? Cost, right, okay. So the cost is what's changing, right? So the cost is, and is it increasing or decreasing? That's a positive rate of change, right? So the cost is increasing by, yeah, 1.54, and it's actually million there, right? Because we're measuring our outputs here in millions. So the cost is increasing by $1.54 million per what? Not per box, okay? That's almost correct, okay? But it's not quite per box because we're measuring our input here in, it's not just boxes, it's what? It's millions of boxes. So it's increasing by $1.54 million per million boxes. Now, actually, if you look at that carefully, though, if that's $1.54 million per million boxes, I might as well say it's increasing by what? Yeah, I might as well just say it's increasing by $1.54 per box. Okay, so what you said was essentially correct, but you have to think about that a little bit. So see, that tells us something. That tells us something about the variable costs. When you're producing 2 million boxes, okay, when you're producing 2 million boxes, that means your total cost is going up by $1.54 per box. So when you're producing 2 million, how much is each box costing you? Let me ask it again, right? So when you're producing 2 million boxes, your cost is going up by $1.54 per box, right? Isn't that what we just said? When we are producing 2 million boxes, the cost is increasing by $1.54 per box. So each box is costing you how much? $1.54, right? Okay. When you're producing 2 million boxes, each box is costing you $1.54, right? Okay. So the material, and when you're producing 2 million, the material and labor for producing a single box is about $1.54. Okay. So that tells you something about your variable costs. What's the variable cost per box when 2 million boxes are being produced? It's $1.54, right? That's how much each box is costing you when you're producing 2 million boxes. Okay. Well, let me say that. That's how much each additional box is costing you when you're producing 2 million boxes. Okay. So when you're producing 2 million boxes and you want to produce one more box, it's going to cost you $1.54 at that production level. Now look, of course, cost is interesting, but more interesting, of course, is profit and revenue. Okay? All right. So we got an idea that, we got a rough idea in that first example how much each box is costing us. So let's think that we're going to sell these things for $4 per box. Okay? All right. So let's write our formula for our revenue function. So we're going to pay $4 per box. We're going to charge $4 per box, okay? So let's write a formula for how much revenue we're going to generate if we sell Q million boxes. I think y'all can write that down pretty easy. If we're charging $4 per box and we sell Q million boxes, how much money are we going to get for that? See, this is what we're charging. 4Q, sure, right, okay, exactly, okay. So there's our very simple revenue formula, okay. If we produce and sell Q million boxes, okay, and we sell each one for $4 per box. Now this is assuming that we sell everything, okay, at $4 per box, then our revenue is going to be 4 times Q, right, okay. Keep in mind this is going to be in millions of dollars. So what's the marginal revenue function? So remember, marginal revenue means rate of change of the revenue. What's the rate of change of 4Q? 4. Yeah, so easy. Nothing to that. Very simple revenue formula. So what's R prime of 2? Well, if you plug 2 into this formula, what do you get? This is R prime, not R. So if you plug 2 into this formula, what do you get? No? 4. Yeah, that's a constant function, right, okay? So it doesn't matter what you plug into that formula, you just get 4, okay? That's a very simple marginal revenue formula, okay? No matter what you plug in, you still get 4. Okay, so I just wanted to show you there that marginal also applies to revenue, okay? All right, now, here's what we're really after. So let's see if we can quickly answer this question, okay? What we really are interested in is profit, all right? So what I really want to know is how much money am I making from the sale of these cookies, okay? So we want to write down a formula for profit, and I'm going to call that P of Q, okay? So how do you calculate profit? What's just the simple way of calculating profit? It's going to be your revenue minus what? Yeah, right, okay? It's just revenue minus your cost. So your profit formula here is so easy, right? Okay? You just take your revenue formula and you subtract off here the profit formula. Your revenue formula, and you subtract off the cost function. Okay? So what was our revenue? That was 4Q, remember? Okay? And what was the cost? Well, we got to write all that down. So what was that? 0.23 what? Q cubed minus 0.98 Q squared plus 2.7 times Q, is that right? And then plus 0.02? Yeah. Okay. So there's our profit formula. Just take your revenue minus the costs. So remember that. Profit is always revenue minus cost. So if we evaluate P of 0, that's easy to do. We can see that really easy. What's going to happen if you plug 0 into this formula for profit? So if you plug 0 in, what have I done with my... Where did I set my clicker? There it is. So if I plug 0 in for Q into this formula, all these terms just disappear, right? And what do I end up with left? Yeah, just the minus 0.02, right? Okay. So P of 0 there is minus 0.02. Profit can be negative, folks. You don't always make money when you're selling items, okay? So what this is telling you is if you're not producing anything, right, you're going to end up losing what? Not 2 million, but 0.2 million, which is 200,000, right? Why do you lose 200,000? Because remember, that was your startup cost, right? So if you still have to pay your startup costs no matter what. So if you pay the startup cost but don't produce anything, right, you won't generate any revenue, so you end up losing that 200,000. Okay. All right, I'm not going to evaluate P of 2 because we're running out of time, but P of 2 is easy to evaluate. That's just the profit you would be making if you manufacture and sell how many cookies? 2 million, right. Okay, so you can do that evaluation, just plug 2 in to the formula. One last thing I want to show you, okay? One last thing I want to show you here, and that's marginal profit, okay? All right, so remember the profit function was the revenue function, right, minus the cost function. So the marginal profit is going to be the rate of change of the revenue minus the rate of change of the cost, okay? So if you want to find the marginal profit, just take your marginal revenue and subtract off your marginal cost. And that will give you the rate of change of the profit. Now, the reason we're interested in marginal profit is because what we're ultimately looking for is where is the profit maximum? Okay? Where is the profit maximum? Here's a graph of that profit function, by the way. Here's the graph of the profit function. Notice you're not always making money, right? Sometimes you're losing money. Then your profit goes up. And notice if you produce too much, you wound up losing money again. So there's the graph of the profit function. And can you see on this graph about where the profit function is highest? It looks like it's about right there, right? Yeah, which looks like somewhere around 3.4 or something like that, right? Okay, just as a guesstimate. So how can we find that exactly where that profit is maximum? Well, that is where the tangent line is going to be what? Horizontal, right. That's where the tangent line is going to be horizontal. And you know where to find where the tangent line is horizontal because that's where the rate of change is what? 0, right. But for profit, what's the rate of change called? Marginal profit. So boy, this is a famous phrase from economics. The profit is going to be maximum where the marginal profit is 0. Where the marginal profit is 0. Okay? So when your marginal profit is 0, that's where your profit is highest. Okay? Is where marginal profit is 0. That's actually, in this example, pretty easy to find. Okay? We think it's right there around 3.4, but we'll have to verify that next time. Is that really exactly right there at 3.4? Okay. Ran over a little bit, but I'll see y'all on Monday. We'll talk more about marginal analysis and your test.